All right, let's get started today. So today is going to be one of the more difficult lessons to understand because we're actually going to be talking about results, the derivation of which is kind of involves mathematics beyond the typical undergraduate level. So there is if you want to derive these results rigorously, it's a lot of stuff, a lot of vector calculus, like integration around the curves and stuff like that, the differential equations, actually partial differential equations. So today we are going to be actually talking about the results not in a mathematically rigorous way, but kind of try to skip the mathematical derivation, but try to give you intuition of what is behind the results. So let's actually start by kind of finishing up some of the stuff we didn't finish on Wednesday, and then get into the more fundamental stuff. Okay, so remember on Wednesday we looked at the stability of an airplane, right? And figured out for the two cases, the green airplane would be stable and the red plane would be unstable. And throughout the derivation, we assumed a bunch of things, right? We assumed that, for example, the increment of CL per increment in the angle of attack is the same for both the wing and the horizontal stabilizer, right? And the lift concentrates on the quarter chord. So actually, these assumptions, and particularly the third assumption, is actually up to debate. So let's actually look at the lifting line theory, what the lifting line theory tells us. And before we go to there, just to think about what the lifting line theory tells us about how does the lift increase as you increase angle of attack. So if you increase the angle of attack, of course we know the lift increases, right? And if the lift increases, how does that affect the vortex? That's both on the wing, both the bound vortex on the wing and the trailing vortex. It increases, right? So, we have said that if lift increases, how much downward momentum in the wake has to increase, and the downward momentum in the wake is induced by the vortices, right? So the vortices has to increase. Now, if the vortices increase in magnitude, that creates a bigger downwash on the wing, right? So actually, how much angle of attack the cross sections of the wing sees doesn't just depend on the angle of attack of the airplane, but also depends on how much induced flow there is on the wing. And the same for the case for the horizontal stabilizer. Actually, the horizontal stabilizer is worse. Why? Because it sits behind the main wing, right? And you're probably going to actually quantitatively do some calculation of how much worse the horizontal stabilizer is being in the wake of the main wing in the homework. But you can immediately see that it actually is in the downwash of the main wing, right? So basically, as the angle of attack increases, how much does the individual cross sections of the wings and the horizontal stabilizer sees as an increase in the cross-sectional angle of attack? It's actually different. Okay, so this actually brings us to this case. Let's watch this video. And in this video, think about why this is a especially bad case for the longitudinal stability, and especially think about how much downwash there might be.
All right, brakes coming in 2, 1.
So this is actually a startup by our department. Most of the people involved in the technical aspect is in our department. If you watch the airplanes take off, you see something special here, right? How short of a runway it took for the airplane to get off. And when you come back, when the airplane comes back to landing, you're going to see it even more dramatically. And if you fly airplanes and land airplanes, we usually try to land on the 9 burst. That means you touch down on the 9 burst. And here you get an airplane that lands on the 9 burst in a different sense. It actually stops on the 9 burst, not actually just a touching down on the 9 burst. Alright, that's it. So, this airplane is really designed to fly in and out of areas that doesn't really have traditional airports, right? And to achieve that, it has to be able to, upon takeoff and landing, be able to fly very slowly. So you get into the kind of same kind of problem we saw when the helicopter flies over, right? The wake, the vertical wake of this airplane would be especially strong, right? There is a lot of downwash. And now if you look at the design of the airplane, it will be pretty obvious. Let's see, where would be a good view? It's not a good view. Look at how high they put the horizontal stabilizer upwards, right? A very good reason for that is if they put the horizontal stabilizer right in between the wingtip vortices, it's going to get a lot of downwash. And what we call like the effectiveness of the horizontal stabilizer is going to be very bad. So going back to the stability, right? So we assumed, for example, the horizontal stabilizer is 20% of the area. I mean, that depends on the design of the airplane. And for this one, the horizontal stabilizer is actually larger than that. It has to be. And the quarter quarter wing is, well, that depends on the design, right? But we really looked at the increment of CL per incrementing angle of attack is the same for the wing and the horizontal stabilizer. In such a case, it's not the case. If you pitch up at slow speed, because of the strong vortices, right? The circulation of the vortex is proportional to what? Is proportional to lift. It's inversely proportional to the span and the flight velocity, right? So, I mean, the span is constrained by like structural reasons, but like the velocity for this airplane at takeoff and landing is so low that the vortices are very strong, and as a result, it induces, as the angle of attack increases, the vortices are going to induce a stronger downward velocity on the horizontal stabilizer, making it less, making the angle of attack, making the increment of CL of the horizontal stabilizer much less than the increment of CL for the main wing itself. Okay, so that's the effect that prevents the horizontal stabilizer from sitting over here. I mean, sitting over here would work if the airplane is flying at higher speed, cruise speed, but it would not work for takeoff and landing at this low speed, right? So, okay, so in the homework question, you don't have to consider this because we're considering an airplane that's flying at like a normal speed. And you actually, when you calculate the downwash, you're actually going to see that the downwash is very small compared to the flight speed of the airplane. But in this case, it's not, right? One is because the flight speed of the airplane is low and the downwash is much stronger. Okay. So this is how lifting line theory affects longitudinal stability. And this afternoon we are going to look at AVL using a software to actually calculate quantitatively, for example, how different designs, different flight velocity would actually affect longitudinal stability. All right, and next week we are going to also look at airfoils. Like the lifter concentrates on the quarter chord is also not going to be correct. I mean, we are assuming this in this homework, but as we start to go into airfoils, we are going to see that this assumption is only true for thin and symmetric airfoils. If you look at for most of the airplanes, the horizontal stabilizer is close to being symmetric and also pretty thin. So for the horizontal stabilizer, this is approximately true, but for the main wing, this assumption is usually pretty bad. All right, so the lifter doesn't concentrate on the quarter chord for the main wing. All right, so we're going to skip all of these and just talk a little bit about not just the longitudinal stability and the lateral stability. So lateral stability is also affected by lifting line theory. So just a brief introduction of what lateral stability is about. So lateral stability is about when the airplane starts to bank. Okay, is there a restorative moment that unbanks the airplane? Right, so just like longitudinal stability is about if the airplane is pitched up or down, is there a restorative force that pitches the airplane back? Lateral stability is when the whole airplane, let's say, banks towards one side. So for example, let's say it's here I can't move the image. So, but let's say it's banked such a way that this is the upward direction. All right. So if the airplane is banked in that way, gravitational force is going to start to work towards the left, right? So if this is upward direction, then the gravity is going to start pointing towards the left. And the wing is still so the lift points orthogonal, right, to the wing. So lift is still pointing upwards. So what is going to be the linear acceleration of the resulting compound force on the airplane? It starts to slide, right? So the airplane is going to start a sliding motion. So this is the sliding. And for airplanes, there is angle of attack. There is also a side slip angle. So I mean, actually, this is the proper name for this is called a side slip. So the side slip angle is the angle between the nose of the airplane and the velocity of the free stream in the sideward direction. Right, it's just take a center plane and look at what is the angle of the velocity relative to that center plane versus the angle of attack is the angle in that center plane. Okay, when the airplane starts to slip sideways, if you look at the flow velocity relative to the airplane, of course, is going to go that way, right? So the flow velocity relative to the plane is going to go in the opposite direction as the direction of the airplane starting to slip. So how does that affect the flow seen by the individual cross sections of this airplane? For example, this airplane has a positive dihedral, right? This sideways velocity actually seen by the individual cross sections is an upward speed, right? So if you project this velocity to two components, if you project the side slip of velocity into two components, one component that is along the spanwise direction of the wing, which doesn't affect the aerodynamics. Okay, if you have a flow, if you have velocity blown from the wingtip towards the wing root, I mean the wing doesn't do anything, right? And the other velocity that's critical is actually upwards. That actually increases the angle of attack, right, of the starboard side wing. Well, if we're looking from the nose. On the other hand, the same sideward velocity, when decomposed in the two directions along the wing and orthogonal to the wing, is actually a downward velocity on the port side wing, right? And that decreases angle of attack. On this side, it increases. Right? The result of that is the lift force on this side is going to be higher. So let's look at the lift force. Higher lift. And as a result of the decreased angle of attack, this side has lower lift. So the overall balance of the lift force is to rotate the airplane backwards, right, towards an upright position. All right. So for example, this is lateral stability, and again lifting line theory. So explaining this doesn't require lifting line theory, right? But lifting line theory actually has to be used to figure out exactly how much higher lift this side has and how much lower lift that side has. Because as soon as you start to have a side slip, the trailing vortex is no longer aligned with the airplane itself, right? If this is the side slip, the wake starts to go towards the right, all right? And the airplane is almost are going to have a non-symmetric sweep, right? So if the airplane has no sweep, and as soon as the airplane starts to slide, it is equivalent as if the right wing, the starboard side of the wing, is going to have a forward sweep, and the port side wing is going to have a backward sweep. And we have already seen how sweep affects, right, the downwash of the airplane. So things like that also has to be taken into consideration in lateral stability. Okay, so this is of course a very qualitative explanation, but like for people to figure out the stability of the airplane, right, you usually need to use a program that has the capability of at least doing lifting line theory, right? Usually using some kind of a vortex lattice method that is basically an improved version of lifting line theory. Okay, so this is again something we'll start to do this afternoon in our AVL section. Okay, any questions about these stabilities? Maybe the only message I'm giving is that lifting line theory actually affects the quantitative result of these stability calculations. Okay, and it's pretty clear why, right? Because all the induced flows that changes as you start to pitch up and down, as you start to slide left and right. Okay. All right, and finally we want to talk about winglets. So winglet is a really clever design. So when we have a strong wingtip vortex, so let's say this is the trailing vortex of the coming out of the wingtip, right? It induces a flow in this direction. So the induced flow on the winglet is going to be in the inward direction if the winglet is upward, and an outward direction if the winglet goes downward. Now imagine if you pitch the winglet in such a way to make the angle of attack to be in such a way that this winglet creates lift. If this winglet creates lift not in the same direction as the induced flow, right? 1 second. If so if the so for example, the wing actually creates lift in the opposite direction as the induced flow. But if the winglet creates lift in the same direction, so let me just write it out. So green is induced flow. And if the lift of the winglet also points in this direction, think about how does this induced flow change the lift vector. Yes? It makes the lift more in this direction. That's also... Yes, it makes the lift more, but more importantly, which direction does it tilt the lift? So for that, maybe it helps looking from up, right? From up, we have the wing and we have the winglet being like an airfoil-like. So if the lift is tilting in this direction and the induced flow is also in this direction, which makes the free stream seen by the airfoil of the winglet to be tilted that way, right? The lift is always orthogonal to the free stream. As a result, the lift vector of the winglet is no longer pointing towards the exact inside, but pointing towards this direction. Right? So again, this is forward. This is the wing. This is the fuselage. So we are looking at the airplane from up. Right? So the winglet, in some sense, creates thrust. Induce the thrust. It's not induce the drag, but induce the thrust. And so this effect is also going to be seen by when you work in the homework. Okay, so if you work on the homework, you're going to see how does the induced flow on the horizontal tail, horizontal stabilizer, actually tilt the lift vector of the horizontal stabilizer. You're also going to see that it tilts the lift. Now the downward lift of the horizontal stabilizer also forward, right? So, but you should also, I mean, if you do the calculation correct, you should see that this tilting forward effect actually is not enough to offset the increased induced drag on the main wing because of the, because like in order to balance the downforce of the tail, right, you have to have more lift on the main wing. So anyway, so this effect actually happens not just on winglets, but also on horizontal stabilizers. Except for the winglet that creates a lift sideways that actually balance each other from left to right, so it doesn't actually create additional harm, unlike the horizontal stabilizer case. Okay, so again, this is completely explainable and designable using lifting line theory. All right. Okay. So so far so good for applications. But the big question we need to answer for all the lifting line theory-based stuff is why, right? We have assumed a lot of stuff. We have assumed, for example, the wake of the airplane is dominated by these trailing vortices, and the trailing vortices come from the wing, right? And there is a bound vortex on the wing. I mean, all of these are kind of pushed down to us without explaining why. So the first question I want to answer is, what is vortex dominated incompressible flow? And then we'll answer the question of like, when do we expect this to happen, and why it happens behind the airplanes. So vortex dominated incompressible flow is also known as potential flow. It satisfies really two criterion. One criterion is the incompressible flow criterion, is that basically if you draw a closed volume, and in 2D it's going to be a closed circle or closed any shape, the flow into that shape, no matter in which direction, it has to balance exactly with the flow out of that closed volume. Okay, so if you integrate the total inward flow, right, basically velocity dot with normal, it has to be exactly equal to the amount of outflow, again velocity dot normal. So that's a completely reasonable because of the air is incompressible, right? So if the amount of air going in is more than the amount going out, that means the air is compressed inside, right? So in our incompressible flow assumption, and when we get to compressible flow, we are going to explain why, right? That we expect the air at low speed to be incompressible. But right now, let's just say if air is incompressible, this is of course true, right? So this is and mathematically speaking, that is basically saying the divergence of velocity equal to zero, right? Or in conservation form, it's saying that the total surface integral of velocity dot with normal has to equal to zero, right? Whenever this is usually we have the normal defined as outwards. So for when this is positive, it's outflow. When this is negative, it's inflow, right? So if you add the positive and the negative inflow together, it has to be equal to zero. So that's basically saying whatever goes in has to go out, exactly, right? So this is number one, and this is easy to understand, right? Whatever goes in has to come out. The second thing is that
Okay, so this is a closed volume. The second thing is whenever you draw a closed curve. So this is a closed curve. Okay. The velocity integrated around that curve. This is not a surface integral, but a line integral. So let's say that curve is let's denote this closed curve as C. Integral around this C. Now velocity dot with dl, which is basically dl is the vector that points from one segment to another. That also has to be equal to 0, unless there is a vortex inside when this integral is equal to the circulation of this vortex, right? Then this integral is equal to the circulation of that vortex. Okay, so we're going to explain where that comes from. And this actually comes from the fact that the whole flow is dominated by something very important, but we haven't talked about. That's pressure. Okay, so all of this is based on the assumption that whatever drives this velocity is pressure and only pressure. But let's first look at why we are saying like a vortex-dominated flow actually satisfies this. So imagine we have a vortex here, right? We have already said that the velocity is purely in this direction, and the magnitude of the velocity is equal to gamma over 2 pi divided by radius, right? So let's just take a curve like that. That's an example of closed curve. It is formed by 4 sides, 2 radial sides, and 2 circumferential sides. And let's make the integration that way. So we are having our dl to be pointed that way. So if we look at that integral, the same integral can be split into 4 sections, right? Over the C. So let's say this is my C. U dot dl can be split into 4 sections. So let's say this is section 1. For section 1, the velocity direction is perpendicular to this dl direction. So the integral is going to be 0, right? So that's for section 1. Now for section 2, the dl direction is exactly in the same direction as the velocity. So the dot product is just a scalar product, right? And the velocity is gamma over 2 pi times the 2 pi times, let's say, this is R0, this is R1. So 2 pi R1, and the length of this is R1 times whatever angle, right? This is the length of the integration. So this is the magnitude of the product, and this is the length of the integration. Alright? And of course R1 cancels out. And now, so this is the second section here. Now the third section is the same as the first section. It's 0 because the velocity and dl is orthogonal. And finally, the fourth section, the velocity and dl is exactly opposite. So we have minus, and the magnitude is 2 pi r0, and the length is r0 theta. So what is the sum? Right, 0, 0, and the plus and minus are exactly the same. So we add up to 0. Right? This is an example of a vortex flow whose circulation of one curve is equal to 0. But this says for all curves. So how about all curves? Now if you have any curve, you can split up. You can so you can always approximate the curve as if it is piecewise. So just to think about this curve as in pixels. But each pixel is in the r theta direction, right? So you can always split the integral of the curve as if, let me just take a curve that contains, let's say, 3 pixels. The 3 pixel would be like that. Okay, and I can split this into, this is 1 pixel, this is second pixel, this is third pixel. The total integration, right, on that curve is actually equal to the integration around these 3 pixels added together, because on the interior ones, whenever you're integrating this direction, on the opposite side, you're integrating in the opposite direction, right? So these all cancel out. So for any curve that doesn't contain the center, right, you can guarantee that the integral is also equal to 0. Okay? And of course, if the curve includes the center, then you just take a middle section, right? Make the middle section excluded. We know the integration around the middle section by the definition of that circulation has to be equal to gamma. And the rest of the integral can be broken up into pixels and integrated 0. So this actually proves that this is true for the flow with a single vortex. Right? And of course, for multiple vortices, it's the same principle, because the integral of a flow field that is equal to the summation of multiple flow fields is actually equal to the summation of the integrals, right? Integral of summation is equal to summation of integrals. That's kind of called the linearity of integral. I mean, it works for integrals, works for derivatives, but does not work for squares, right? And as we are going to go, so we are soon going to start talking about pressures and the Bernoulli's, right? I mean, there is a square in Bernoulli's law, and they are going to soon find out the pressure so if you figure out the pressure of one flow field and the pressure of 2 flow fields, if you add them together, the pressure is not equal to the sum of the 2 pressures. But for velocity and integrals and derivatives, that all works. Okay. Any questions on this special example, demonstrating why both property 1 and the property 2 is true? Right. Property 1 is true. Almost obvious, but like, of course, you can go home and do the same thing with these kind of pixels. Okay? All right, no questions? I'm always nervous when I get no questions. Sometimes it means nobody gets it. Okay, good? All right. Okay, so let's figure out why property 2 is true. For property 1, it's incompressibility, it's obvious. But for property 2, now is the first time we start to talk about the Navier-Stokes equation. And because this equation sounds scary, and actually it is if you write it in full. So I'm going to introduce it using something that everybody knows, Archimedes' principle, right? What is Archimedes' principle? It's just that if you put something in water or in any fluid, right, you get upward force, right? And the force is equal to the weight of the fluid that like this object occupies. Right, so this is not fluid dynamics, but fluid statics. Okay, so does anybody still remembers or have ever looked at why is Archimedes' principle true? Like, where does that force come from? Like, when you put something in water, why does it, where does the flotation force come from? Exactly, different heights have different pressure. Okay, so if you immerse something in water, so the bottom of that something has high pressure, the top of that thing has low pressure, and then as a result, the force exerted on the object is basically what we call a pressure gradient force. What is pressure gradient? Gradient is basically a vector that points from low area to high area, right? in the direction orthogonal to the contours or the isosurfaces if it's in 3D, right? Okay, so in fluid statics, nothing is moving, right? So what is the pressure contours? It's exactly horizontal, right? The pressure, as you go lower, you have higher pressure, right? So the pressure gradient points exactly in the downward direction. Okay? So the pressure gradient force the pressure gradient force is always proportional to the minus of the pressure gradient. So unlike the gradient, and it's just a mathematical definition, points from the low area to high area, right? The pressure force is opposite to that. It points from the high pressure to low pressure, right? I mean, everything is squeezed by high pressure, away from the high pressure into the low pressure, sucked into low pressure, right? So the force goes like minus grad P in the direction, okay? But what is exactly the amount of force? Well, the amount of force, think about what is grad P, what unit is grad P, right? Pressure is force per area. Now, if you take the derivative, take the gradient of pressure, right? You're dividing that unit further by length, right? So grad P is force per what? Volume, right? So grad P minus grad P is actually the pressure gradient force per unit volume. Okay? So next time when you see the Archimedes' principle, right? Like, why is the force proportional to the size of the object, right? Occupied by it's actually, the Archimedes principle says it's the mass of the, it's the weight of the object. So it's the volume times mg, right? It's the volume times rho g, right? Rho is the density of the fluid, the g is gravitational constant. But what is rho g? Rho g is actually the pressure gradient, right? Okay, rho g is nothing other than the pressure gradient. So the total pressure force is grad P times volume. Okay. So the Navier-Stokes equation is simply an extension of that force, but it is basically lumping in the pressure gradient force with Newton's law. So it is basically saying that the acceleration du, velocity is a vector, dt. So this is acceleration or time derivative of velocity of a fluid particle, right, is equal to the force, let me just say grad P times the volume of the particle divided by the mass of that particle, right? And we know for a fluid with uniform density, that's just grad P divided by rho, right? M over, let me just say volume to distinguish it from velocity. So the mass over volume is the density of the fluid. So this equation, du dt equal to minus grad P over rho, is the first version of our Navier-Stokes equation, right? It's just the acceleration equal to the pressure force. One thing you have to get used to is that whenever you have force per volume, right, you get acceleration by dividing force by volume by density, which is mass per volume, right? So that's basically it. Okay? So now how does this lead to the fact that there is no circular integral? So this circular integral over a closed volume, u dl, is actually called a circulation, right? It's not a circulation, it's the same word as the circulation of a vortex, but it's basically a circulation over a curve. And what is the circulation? If the curve encloses a vortex, that circulation is the same as the circulation, and actually it's used to define the circulation of a vortex. So why is circulation equal to 0? It is because this thing actually, if you look at the time derivative of this thing, Okay, on the Navier-Stokes equation, this is actually equal to the time derivative. So you can actually move this time derivative in, right? You can. So okay, so this is du dt times dl, and use the Navier-Stokes equation. And if density is constant, that moves out of that, and you get minus of grad p dl. Right? You are integrating a pressure gradient over a closed curve. And in mathematics, I don't know how much vector calculus you did, but like whenever you're integrating around a closed curve of a gradient of something, well, if you integrate over a curve of a gradient, you get the difference of that thing between the two ends of the curve, right? If you integrate, for example, in this case, right, over a curve of this pressure gradient, you actually get the difference between the pressure here and the pressure here. And the special case of that is if you integrate this around a closed curve, you get the difference between the pressure at the same point and the same point, which is 0. Okay, so what that tells us is that if I have a curve that has no circulation to start with, for example, very far ahead of the airplane, right? Nothing is moving, velocity equal to 0. Integrating over any curve, you get 0 circulation. And now you allow that curve to move closer and closer to the airplane with the air. So, by the way, this derivative, like when we derive this, right? This derivative is the derivative of the same fluid particle, right? So you cannot say, so basically we are taking this is the rate of change as we are following the same fluid particle, right? Okay, which means this derivative is the rate of change as we are following the same fluid that's making up the curve. Okay, so as if you take the frame of reference of the airplane, there is a curve very far ahead of me, and it's comes towards the airplane as the air is moving towards me, and it goes over the airplane to its wake. As long as that curve is not broken up by my wing or by part of the airplane, right? This is always going to be true, and that curve stays 0 circulation. Okay, that's basically why we have this vortex-dominated flow. And I said except, because if that curve is broken up by the wing, then there is a problem with this equation, that this equation only considers the pressure force, right? It did not consider, for example, the air interacting with the wing. I mean, when the air, in reality, when the air goes very close to a wing, right, it gets viscous effects, it gets dragged down by the wing, etc. So we're going to look at this when we get closer, when we zoom closer to the wing. But like, if the curve doesn't interact with the wing, then when it gets to the wake, it has no circulation. Okay, and the only time the circular contour gets any circulation is when it's broken up by the wing. Okay, that is why when we are looking at the far wake of an airplane, so let's say this is my airplane and I'm looking from the wake, right? If I draw something over here, so this is my contour in the wake, I should expect no circulation. If I draw a curve here, I expect no circulation. If I even if I draw a curve like this, right, I should also expect no circulation, even if the curve is around the airplane, right? And I would only expect a non-zero circulation if my curve is like that. Alright, so what does this mean? What this means is there is only non-zero circulation. Let me just use a different color. There is only non-zero. I would only expect the vortices to concentrate on one plane, and this plane is basically the small fraction of air that came in close contact with the airplane itself. I don't know if I explained it clearly, right? So basically, there is going to be all the locations with non-zero circulation is concentrated in a very thin, like we call vortex sheet coming out of the airplane. And that's basically what lifting line theory is working with. The only assumption that's not strictly true about the lifting line theory is actually twofold. One is that this vortex sheet did not deform. And another aspect of the Navier-Stokes equation I didn't talk about actually makes intuitive sense is that all the vortices, once you have a vorticity, right, once you have a vortex, the vortex has to follow the fluid particle, right? The vortex wouldn't jump from one fluid particle to to some other location. It always follows the fluid particle. So the vortices follow the velocity. But the velocity, because of the induced flow, they actually deform itself, right? So lifting line theory really works in the case where works very well in the case where the induced velocity is small relative to the free stream, right? Actually, for the video we watched for electro, actually lifting line theory did not work very well unless you consider the deformation of the vortex sheet. And the second is there is no viscous effect, right? And although the viscous effect away from the airplane is small, but as you trace the wake for a long time, still viscous effect works in. So the vortex sheet is not going to stay as a sheet for a very, very long time. So, but lifting line theory basically works when the vortex sheet gets not as much deformation and you are not looking at too far away, too much in the wake of an airplane. Okay, let's actually look a little bit on the consequence of such vortex-dominated flow. Yes, question?
So for this big thing that contains the airplane itself, like we have two vortices to the opposite direction.
Yes.
So we assume that they cancel, but we can still write this equation, right? About
Yeah, very good point. Okay, so I should have explained that, right? So if you have a big circle that surrounds the whole airplane, all this derivation is still true, right? I mean, because the big circle never came close to the airplane. So this is still true. There is only pressure force. And this circulation is zero initially, so it stays zero. So what's happening is that in the wake, there are counter-rotating vortices from this side and from this side, right? So in the contour, the circulation of the contour is equal to the summation of the circulation of the vortices within that contour. If you have counter-rotating vortices, they sum up to zero. That is why over this big contour, there is zero circulation. And this is also why the trailing vortices of an airplane has to match each other, right? They have to sum up to zero if you consider the sign of these vortices. Okay. Other questions?
the thing was that, like, for that case, can we really, is the Navier-Stokes equation true?
Yes, the Navier-Stokes equation is true, right? Because, well, I should say the Navier-Stokes equation, considering only pressure force, is true. Yeah, you should only consider other forces when you are getting very close to the airplane. You have viscous effects, right? Otherwise, yeah, this is always going to be true. And another thing is for the speed of the airplane, for the speed of usual airplanes, the pressure force is. I mean, you can do a little bit of calculation to figure out how big the pressure force is. Usually, it's much, much bigger than the pressure force you have induced by gravity, right? If you compare that to rho g, where rho is the density of air, it's this pressure gradient around the typical airplanes are much, much larger. So you can also ignore any gravitational forces. But even if you have gravitational forces, they are usually pretty much balanced with the pressure gradient caused by the different heights, right? So for aerodynamics, throughout this whole subject, we're going to ignore gravitational forces on air, right? Gravitational forces on airplane cannot be neglected, but on air, we're going to neglect it. All right. Okay. Maybe we should come up, do some consequences later. But you remember just one thing. One thing is that we integrated over an infinitely large line, right? So what is the integral of the downwash over dz, right? From minus infinity to infinity. We said that is equal to gamma, right? And now we can start to explain that equation using circulation. Just imagine I zoom out of the picture. So let me see if I can actually zoom out of the picture a lot. Okay, so these vortices are tiny now. And this line, I just loop around this. The velocity on this loop around line is going to be tiny. It's negligible, right? But this total, so that means this integral is basically approximately equal to this circular integral of actually u dot dl, right? So here we are using the vertical velocity because this line is vertical, right? So this is just a w, not a vector. So w is the vertical component of the induced velocity. It is it is actually equal to u dot dl if the dl is in this direction. So by just as simple as that, we have actually proved what we spend a lot of time doing calculus with, right? So this is equal to gamma just by the fact that this curve includes this single vortex but not the other. Equivalently, you can do it this way, you get the same result. And if you look at the outer curve that encloses both, you're going to get 0. Okay? So we're going to further use things like that starting from next lecture, and as we zoom closer and closer into airplanes. Okay? All right, see you in the afternoon in an hour for the AVL.
An entire big circle around.
Zero.
Because they cancel.
Yeah, because it's the sum of the circulation inside. Yeah, one positive, one negative is going to be 0. Yeah.